Hey everyone, I'm excited for today's topic, sign language recognition. Ming Rutar joins us today to talk about how computer vision can translate words into text. Her objective is to get 178 words recognized correctly. You're going to have to stick around to see how she did. And if you like this video, please comment to help us out. Thanks for joining.
And with this academic depth, and you also get all the hands-on practice on those technologies. And the right is just the things what I know about the Udacity, and we can, if people are interested, we can talk about later. So this is a task. Here's the video. I show this. So you see down there the translation, John, and in one by one, fish won't eat but can eat chicken. So we're trying to get this woman's suggestion into language, and now we want to see how that works. The one thing I want to explain here is that nowadays, I think last year or so, we have this like tagged videos. So the machine learning watch the video and translate it into English. But this project was done back in 90 something. At that time, we don't have that. Technology is not that advanced yet. So what we do is first translate. It's the first, the information is extract from the video. We get to understand that, that is the, I think, the core of the artificial intelligence. They mimic how we work, human works. And when we see this, the hand wave, the sign language, what we see, we pay attention to the hands, right? So here we pay, but how computer knows where the hand position is. So the computer is not really reading this videos. It is a position where the hand is. So like what you see here, here you see this this yellow square there. That is where show where the hand is. And this is, I think, the things what Gary taught a couple weeks back. It talked about the computer vision. That's how they captured.
Is it, so I looked at this earlier, is it capturing both hands or just one?
In this case, it's one, but actually the data is in the data, it's actually two hands. So we capture the two hands position and plus the nose position. Nose is used as a reference. So this way, this way, it is in the center, and you can do more things. Because this we call like raw data input, left hand position, right hand position, nose position. And from that position is what we will get is the, this is how they look like in the video. And this is a feature extraction. In the machine learning and in the deep learning, this is very much like half the work. You identify the features. And the machine learning model actually is taking the features data. It's not watch the video. It's not the feature. It's not actually the raw data input. It's a feature extracted from raw data. It feed into the machine models, and the train the machine models. And then when you have the machine model to identify something, it's also using these features. That's very important, very key on the feature extraction. So this, but feature extraction is really not that mysterious. It's really common sense. How you want to do it? So here, this is one way. It's like a feature graph, and that is the distance between the nose and the hands. The GRX, the right hand distance. It's the nose as the references, and then it is this y Y of the left hand, Y of the right hand, and the X, so that's the data we extract. But then there's other way to do it. This is taking the polar value, the feature polar. And this is this one actually switched it's using the opposite tangent 2 algorithm, but it has XY switched. So it's using the distance and the angle. And here is just algorithm. You can see the algorithm very simple, just the nodes, the distance and the square, then the square root. It's very simple algorithm to extract it. Then there's others like using the difference between the frame and the video is a set of video pictures, right? So it's a difference between two pictures. That's the other way. And we're also using more like I do using those the polar work better. So polar plus the differences between the frame between pictures frames. So you can come up with all kinds of idea how you want to extract data. Some of the hand distance between the hands. You skip the nose.
It's a reference point. And a distance from the nose.
Two hands. No, you have another way. It's another kind of features you can deal with it, like difference between hands. Yeah. That's the other way also to do it. You can be very creative. You just like the feature what most represent, make it distinct. So I said this is more common sense. But the extract the feature data, there's a technique to make it more suitable for machine, because those are data feed into machines, so you need to adjust to machine's taste. So that you normalize it, you scale it, make the data what easier for machine to digest. So that is what to me, that's what the feature extraction is. Yes, but those are techniques. Normally they have pretty standard ways how to make the data. The scientists studied and know what machine likes. So they get techniques that you can apply them, like the scale it, normalize the data. So because the human somebody have long arms, somebody have short arms. So just to make the data more normalized so the machine don't get confused. We like to see a person, we see it immediately, right? But it's important for the machine how to see it. And the other important part is select the models. It is the model, you train the model and have the model to predict, to do the work, right? Inference, it's the model do the work. And here what we're using is the HMMLearn. It is a library. It's not like a TensorFlow or the Torch framework. This is a library. And the HMM is unsupervised learning. And what the HMM stands for is the hidden Markov models. This is the Bayesian network presentation. And the Bayesian network is, narrow networks basically is also have this Bayesian network kind of presentation. It is the probability from the one nodes, like the nodes C0, what's the probability go to C1, what's the probability go to the A2. So this is all the probability things. So this entire network is, it's like that. It's like, I mean, there's what probability go to this way, what probability go that way. It's more like fit our human kind of way thinking. I think that 90% of the time we're not, 90% of the time I think we like a lot more lean toward this than the other. And the early time, there's other the AI fields, they were like true or false. Just that everything is true, black, white, true or false. And it be proved that then quite applicable because most of the time we're not that clear, like the court, true one or the other way. Yeah. So the Bayesian network makes much more sense. And inside, once this is just explaining how it actually works. So inside the HMMLearn, you provide this Geyser HMM model, and you can see it. Okay, this is what we see. And what we use is like this Bayesian network, but ignore this part, just like one line. And they call this Markov chain. So from this, it's just like all C's. And those middles we call the hidden layer, hidden state. And in this picture, here's a state 1, 0, 1, 2. These are the hidden states. That is where they absorb the knowledge. So what we do is we try to train them using the Geyser HMM and train it with a different number of the hidden state, and then we compare them to see which one is the best. So with the same data set, actually it went through, I think we did like from 3 to 14 hidden states. So each of them we had that like 11 or 12 actually, 12 models actually spelled out, then we pick the best. And this Geyser HMM, you have this function called, you initiate with the things like how many iterations to train and how many the hidden state I just explained will be you want it to be. And then it have the matches to fit. That's where you fit in this the data for the training, and that is what the feature data what we extracted. And then it is later called the score-based inference. It will say percentage probability for their words. Okay, the other thing I need to explain the data. I like to skip the one thing here. The video input. I think I actually didn't skip. Oh, here. So here, see, this is a John Wright homework, and here they have. This is how we have the video, then we have the metadata and explaining which one is a John, what the words are. So here say this is in the video 1, and from the frame 8 to 17 is John, and then it is from a video 3, and this is I picked a bad one. C is bad. See that it's like from this one, like the word C is the video 3, eclipse 3, and the frame 12 to 20. And then for each of these data, we have here the video and the frame and the coordinates of the left hand, right hand, and the nose. And also the information of the speakers. And the information about speakers is important for the data normalization because the arm could be different length, and some people wave more, some people wave less. And so this is for the average for that person, then you normalize by that average or the standard deviation. It does different techniques for the normalization. So now I think now we know that. So we feed into so we from this data, right? We extract those information, those feature information, and we feed those information into the model, and we're building the data set like John, and this is the sequence of the feature, the videos in the videos for the John, and there's a multi appearance in those videos of the John. So we feed all of them. We get all of them and feed into the model for training. And in the machine learning, when you do the training, it's important you get the training, then you do the testing. And normally when you do the data scramble, you have to divide it. But in this case, they already prepared for us. There was a set of them. We already just have those common separate the value files just to read them in. So this is a kind of start from some kind of middle to do the trainings, and then all the data preparation, which is actually is much more hard than I think to the training, and those was done for us, either by the source or by the university staff. Yeah, we do the fun part. Yeah, so we train the model one word at a time with the training data. Now I explained what the training data is. Then the words are encoded. Again, that is the John is difficult for machine to digest. So we say one is the John, machine only know one. And then the machine, after when the machine inferred, they say like a 1, 3, 4, like that kind of sequence. Then we translate it back to the human words. That's the how it works. And then each word have associated a list of a feature set, because as we see, the feature is not one film, not one frame in the video. It is a set of the frame. Remember, there was 12 to like 14 something. And then we train this national HMM models, and with that word sequence, and then we compare, we try to pick the best one. And then, so each word has a model associated. After we get to each word has a model, right? And now we use that model to try on the test data. And the test data, the input look at the same, but we did a little bit clever here. Test data, we basically make it like test on the sentence. It looks like a sentence, but actually the model is one by one. It trying to identify one by one. It didn't understand the correlation between the words. And yeah, okay, let's see. So as I said, in the model we do in the Gaussian HMM, but it is very rough. If you don't do any manipulation there, the results, we have like 178 sentences in the test data, and the raw Gaussian model only recognizes like 58 words. So the error rate, that is the one with a mistake, is 67%. Yeah, and to pass this course, we have to have like less than the 60 error rate. So there was two popular, like they call information criteria on the how to select the score. The one is called the Bayesian information criteria, BIC we call it. And the way the purpose of it is to punish the word have a lot of training data to reduce a little bit its score. So this was like not to get into the overfitting. In the machine learning, the overfitting is always a problem. So it can identify set of the known things very, very well, but it's like an idiot when you see something it haven't seen before. Because it's like the human would memorize things. Like I call that ring man kind of thing. But so we want this network able to think. And to prevent it, that is what the Bayesian, to prevent the overfitting, that is what the Bayesian formula is. And this is the link to that, to a very good slides talk about it. But this is a formula. The P is a magic. The other is like, this is a Gaussian score, okay? This is the HMMLearn of the words. This is kind of okay. These are the all fixed things. And this P, my God, I had two of them. I found two of them. And the first one wasn't that good. And it's like half of my features didn't pass this 60% score. But then magically I found another one. It was just the formula a little bit twisted, just a little bit twisted. And the second one is like all my features pass that 60%. It's and like the lots of things in the machine learning, it's like you don't ask why. People figure out. Sometimes people try to interpret it. Sometimes the results after phenomena after the X saw the results. So there's a lot of experiments needed with the machine learning, and also I think that is the importance of why it needs that much academic background, because you're searching something, but the academic background kind of give you a direction to search, kind of narrow it. You have to search anyway. It's a much narrow field, and this academic instance kind of guide you to a more correct path. And the discriminative information criteria is much more straightforward. I get to the model, and I try, because remember we have a different number of the state, right? I try to score this word I'm using, but also I try with all the rest words and the scores. I say try to get the score. And now, in my case, I did was for all the rest, the scores, I did the average of them. And then I see my score with the average score, what the differences. The one gets the largest differences. I say, oh yeah, that's a good model to see my word better. But you can have a different way to do how you determine this distance, and it is discriminating the others. That's why discriminative information criteria. Mine was using the average, and I think my results is also kind of average. Then my magic big two beat this dick by dick. Yeah, it's amazing, but people can adjust. Dick is more intuition. I think the Bayesian, I don't know if it's a math on it or it's Bayesian, just more magic to me. So this is, Dick is, I did was the like average, but you could have another word very close, but then another two words very kind of close, but the other word is very, very low. The average is still pretty low, but actually that is a bad model. You can have a lot of manipulation there, what I want to say. Okay, what is, so this is so the way how we do it is I have to building this here to test it. We're building a recognizer, and what recognizer do is with the feature and with the selector, combine them together and try it. And the results basically is here. And we try it with the test data. It is one sentence at a time. And the model, basically every word fed in, it will try all the models. And so you can see this is really a school project because we only have 178 words there. If you, in the real world, you get lots of more words, it's probably need lots of optimization there. Yeah. So we try all of them. So you get to this table of the word and its score. And now we pick the highest score for each of them. That is how, yes, how we come up with the word. So this one is, I have the orange, that is the 2. That is my magic 2, because my reviewer say that actually he said it should be the one what I tried before, the magic, the 1, my formula, big formula 1. But, and this is a scaled Podell. Podell is the polar plus the delta in the time. And this is the error rate is 43, so it recognized the 57%. And see, this is, so this one was John writing homework. It's correct, 100%. This one. Yeah, it was amazing. It was amazing to see it. And then where the star is, it's actually kind of wrong.
Proper
Yeah. And it was recognized one word at a time. It didn't know the next is right. Right.
Okay.
Yes. And always also is always pick just the top score. Yeah, it was amazing. And I didn't and using the deck, I have in my files. With the deck, you actually they recognize kind of like a different set of the way, what the big make mistake, big maybe pick the correct way. And I didn't. I probably could try.
It probably increase your probability.
Yeah,
Decrease your error rate.
yes, if you have, because we have the score list for all 178 words or what, for all of them, right? So now you can have, I can have pick the top 5 from the big, top 5 from the dick, and then see which one makes more sense, right? That's need another kind of algorithm to pick it, optimization kind of things, and that's probably going to score better than this. And all this, oh, that's my results. So, so one thing I want to point out is this is like the feature Podell, and then this is a scaled feature Podell. This first one and the last one. This just scaled it, and the difference is like recognize 101 instead of 89. So you see the differences of those techniques to normalize data to scale data.
Yeah, you passed every one of them.
I did. And those are not only things I have an experiment. I have experimented more than that, double that list. Yeah, it was lots of fun to try.
82.
Yeah. The best is recognize 106, and with this kind of technique, I think the talk is you can never have error rate under probably 30% or 40%. You can never get that because we recognize one word at a time. So normally with this, this is basically it's a synthesized words, right? Okay. So what we use, people what use is a natural language model. So natural language model, I didn't try it because of kind of around at the time. Natural language model basically is say, John write, that is correct. But if you say, and John marry, maybe not, or John and have the English the after that, it's not correct English grammar. That's the natural language what to do it. And the natural language, they call the grammar, like 2 gram, 3 gram, and n gram. So the 2 gram is you put 2 words in order and ask, give you like, is correct English or not? I think it's true or false. No, return. But n gram is you pass n words into it. And so you can imagine that n gram is going to be really slow. So I was thinking to do that 2 gram, but I didn't get a chance to do it. The file for the natural, you file for the natural language, have to kind of relevant to this context, right? So you can find you have to have John there, you have to have the visit and have a married, what would have here, to get to be good in that. So I didn't quite know how to read that file and didn't get to help.
Why are there asterisks on some of the words there?
This is wrong.
Just it didn't catch it. Okay.
Didn't catch it. Yeah, and see, this was quite wrong. Yeah. Yeah, so, oh, sorry. Oh. You see, this is like they basically compare the new set of the data, compare if how much it match with this curve inside outside. So that's they give the score. So if the curve kind of narrow, it's better to detect because if you're in, it is yeah. Yeah, that's all I have for this presentation.
I hope you enjoyed our topic today. If you'd like to see more of these videos, be sure to comment and subscribe to get notified of future videos. Or go to our website, knowledgemavens.org, and subscribe to our mailing list. That way you can get notified of topics, invites, videos, codes, slides, and much more every single week. Until next time, cheers.